Okay, let's solve the following problem. A rigid pipe of length L is to be transported through a corner in a tunnel. Assume the pipe cannot be oriented vertically and must move through the corner in the orientation as shown below. The diagram is a floor plan of the tunnel illustrating a view from above looking down on the pipe and the corner in the tunnel. In addition, each of the two parts of the tunnel have different widths. The width distance A is 19 feet. That's 19 feet here. And the distance B, that's equal to 12 feet, and that's the distance here. So the question is down here, find the maximum pipe length L in feet that can be transported through the tunnel corner with dimensions as given. Okay, so now to sort of develop some intuition and understanding of the scenario in this particular question, let's take a look at an example here with this blue segment representing this length of pipe that's in this corner in this tunnel, and we're trying to rotate it through the corner. And so imagine that we kind of have it fixed at this sort of pivot point where it's going to travel around the corner, but in my animation that I'm using here, I'm changing the lengths, and it's kind of ironic that the largest length that can actually fit is the smallest of the different lengths that I'm calculating, right? So a length such as this, it wouldn't make it around the corner at that particular angle because that length is too big that at any other angle, um, a length larger than that wouldn't have fit, right? So it's only the smallest of all these lengths that would fit at every other possible angle, right? So this angle theta that I'm referring to is the angle that's right here, and I'm imagining now as I change through all these possible angles going from 0 degrees up to 90 degrees, I get these very different length pipes, and it's only the smallest of all those lengths that would actually fit at every angle in between 0 and 90 degrees, right? An angle like at an angle there at 60 degrees with a length of 51.9, I know that as I try to pivot around that corner, the lengths of that segment are going to be smaller, and a length of 51.9 wouldn't fit. So what we'll do is we'll develop an equation that determines the length of the entire pipe as a function of that angle theta at that pivot point, and we'll need to find the smallest length as a function of that angle theta, and that smallest length is the largest that would possibly fit at any other angle as we rotate about that point. Okay, so here's where we have that angle theta, and this length L, I'll break it up into two parts. Let's call this L1 from here to here, and then we'll make L2 the other part, so that the full length that I'm looking for is L1 plus L2. And now what I'll do is I'll develop formulas for L1 and for L2. And we'll use some trigonometry to do that. So let's recognize that they're giving me the distance A equal to 19. So across here, I have a distance of 19, and therefore I can actually identify a right triangle and also recognize that this distance here is 19, and the angle that I have here is theta. Now this angle, those are vertical angles, they're equal. So I recognize that this is also theta, and because this is 19, I can use the cosine function. And I could write the cosine of theta is the adjacent side, 19, over the length L1. And that's how I can solve for L1. While I'm at it, I also know that over here, this distance, this is B, and that's 12. So if I have 12 here, well, I can use the sine function. The sine function will involve that length 12. So I'll say the sine of theta is 12 over L2. And it's from here that I can solve for L1. I'll write L1 cos theta is 19. So I can write L1 is 19 over the cosine of theta. And from my second equation, I'll say L2, that's sine theta. L2 times sine theta would be 12. So L2, that would be 12 over sine theta. So now I know that L is this L1 length plus the L2 length, so it's 19 over cos theta plus 12 over sine theta. And that means my length as a function of theta can be written as 19 secant theta and 12 cosecant theta. Now we saw how the angle theta, as that changes, the total length changes, and we're actually going to look for a critical point where we actually have a minimum for the length L, and that minimum for the function L is actually the largest pipe that would actually fit at all the other angles theta besides just at that critical point. So let's do a derivative here. So L prime, that would be 19 times the derivative of secant, that's secant theta tangent theta. And then we have the constant 12 times the derivative of cosecant, and that's negative cosecant theta cotangent theta. So our derivative is 19 secant theta tan theta minus 12 cosecant theta cotangent theta. And I'm looking for a critical point so that I can find a minimum. That's when the derivative is equal to 0. 0 equals 19 secant theta tan theta minus 12 cosecant theta cotangent theta. Now this could look like really a formidable kind of an equation to solve, but actually if we write it back in terms of sines and cosines, it turns out to be not that bad to solve. So let's say we have 0 is, we got 19, that's 1 over cos, and this is sine theta over cos theta. And then we have minus 12, this is 1 over sine theta, and the cotangent, that's cosine theta over sine theta. So what I can do here in order to solve this is recognize that we have some restrictions on the values of theta. Remember that theta is going to be between 0 and 90 degrees. At a minimum, it's 0. At a maximum, it's 90. And those represent extremes in the value of L. L would be essentially infinite if theta was 0. And if theta was 90, once again, the length would be infinite. So it's going to be always theta between 0 and 90. And because of that, we know something about the how we can solve this, because these guys are always going to be non-zero. The cosine of theta will never be 0 when you stay between 0 and 90, right? So we're assuming that theta is strictly between 0 degrees and 90 degrees, and that means that the cosine is not going to be 0 and the sine is not 0. Since neither of those are 0, what I'll do is I'll move both, rather than trying to factor it or something, I'll just move one of these terms. Let's take this one since it's negative, move it to the other side of the equation. So it turns into 12 cos theta over sine squared theta equal to 19 sine theta over cosine squared theta. And once again, because these quantities aren't 0, I can just multiply both sides by those values and assume that I still have legitimate solutions. And so, in fact, rather than just multiplying both sides by the common denominator, I'll just say that effectively the result is the same as if you cross multiply these. So we end up with 19 sine cubed theta is 12 cosine cubed theta. Under the assumption that sine and cosine are not 0, we can reach this equation. And then we can move this back into tangent, because then we can use the calculator to get a solution with tangent, more convenient. So we'll say sine cubed theta over cos cubed theta would have to be 12 over 19. And that is tangent cubed theta would have to be 12 over 19. And that means, well, we could take a cube root of both sides to isolate tangent. So the tangent of theta would have to be the cube root of 12 over 19. And then knowing that the angle is something between 0 and 90 degrees, I could just go right to the tan inverse on the calculator and find the angle that satisfies this. So we end up with theta is tan inverse of the cube root of this 12 over 19. And that's something we can just estimate on the calculator. Make sure, well, it doesn't really matter whether you're in degree mode or radian mode. Maybe degree mode is nice because it's a little bit easier to visualize and therefore catch a simple mistake. So I'll keep it in degree mode here, and typing that into the calculator, I get about 40.6 degrees. Now, if both hallways or both sides of this, both halls of this tunnel had been the same, this angle would have come out to be 45 degrees, right where you have the minimum. But it's not 45 degrees in general when these two hallways or halls in the tunnel are different widths. We'll get something other than 45 degrees there. That's not my answer, of course. What I want to do is find the length that corresponds to that angle. So I'll just go back to what L was. It was the L1 length plus the L2 length, and what were those values? So I'm now looking at the length as a function of theta, and if I found the critical point, actually that's a critical point. That doesn't prove that it's a minimum, so we could actually look at some angles that are close to that and confirm that it's actually a minimum, or we could look at the sign of the derivative and see that it's negative and then positive again. But that's the only critical point. That's where the minimum occurs. So we'll just plug in that angle of 40.6 degrees. So 19 over cos 40.6, 12 over sine 40.6, and estimate that, again, making sure that you're in the right mode. I'm using my angles here in degrees, so, and it's closer to 40.62 or maybe 40.63 if I was a little more accurate. Let's say 40.63. So putting in 40.63 just to be a little more accurate here. 19 divided by cosine 40.63. And that'll just right away add to that 12 divided by the sine of 40.63. This comes out to about 43.46 in feet. So that's about the minimum there. So since that's the minimum L value for all the different angles that correspond in that rotation about that pivot point, that 43 is the biggest that would actually fit. So trying that value here, 43.46, and that's it. That's what it was looking for. Okay, so that interactive that I had created to illustrate the problem, the values that I picked here are pretty close to the numbers that were in this particular example. So let's see, this is not, these values aren't calculating exactly, but I know that the angle that we came up with here, we got an angle of about 40.63, and at an angle of 40.63, the length was 43.46. So let's confirm that. If I go through and look at all these different lengths, a length of, let's say, 49 isn't going to fit because as we rotate around, it's too big, right? But so what I'm looking for is a minimum value. I see the length going down as I approach an angle of 40, and then now it's going up again, right? 43. So I can see just by going through all these different lengths that the minimum appears to be around 43 something. In fact, it looks like I can get about 43 the lowest I can get is about 43.46, right around there. And that's happening at about an angle of 40.6, roughly 40.6. Again, this is not super exact in the way it was constructed, but it's matching pretty well with the exact solution that we had done using derivatives. Okay, that's it. Hope this was helpful.